Today we are going to start on Chapter 5. The beginning of this chapter will seem like review if you've seen the dot product before, and I'm kind of assuming that everybody has actually seen that before since we talk about the dot product in Calculus 2 and Trigonometry here at Wichita State. But we will be generalizing the dot product and applying it to some problems you probably haven't seen before. So just to kind of start off here, the dot product is a way to multiply two vectors to get a number. In R3, if we say have a vector x1, x2, x3, just say this is the vector x, and we want to take its dot product with a vector y1, y2, y3, which we'll call y, then their product is just the single number x1 times y1, then x2 times y2 added to that, and then x3 times y3 added to that. So we're taking in two vectors and their product is just a number. We can actually view this instead as a matrix product. Let's say that we have the row vector x1, x2, x3, and we multiply that by the column vector y1, y2, y3. What we get is because we're taking a 1 by 3 vector multiplied by a 3 by 1 vector, we're going to get a 1 by 1 vector. And the one element that's in there, the one entry, is exactly the same product that we see up above, the same x1, y1 plus x2, y2 plus x3, y3. And since it's only one number in a 1 by 1 matrix, we're just going to just say it is that number. We're not going to put it parentheses around it or anything like that. Well, okay, so how do we want to think about this? Well, in linear algebra, we're considering our column vectors as the actual elements of R3. So this vector y, as we've written it, is in fact the vector y. These x's over here, this is kind of the wrong orientation. What we should really do is think about this as the column vector x1, x2, x3, but then transposed. Think about this as x transpose times y. So this is, well, it's exactly what we have written up above. The x transpose is the row vector with the x's in it. Y is just the column vector with the y's in it. And x transpose y is now this value over here. We can generalize this idea to any Rn. We just have to do the same kind of thing. So that gives us this definition here. For two vectors x and y in Rn, they are n by 1 column vectors, and we can form a matrix product by taking the transpose of x times y, and the result is a 1 by 1 matrix that we're just going to consider just a number. We're not going to worry about parentheses there or specifying that it is still a matrix, because that's not really too important. In fact, it's more useful to think of it as a number because that will allow us to do more things with it than we can with matrices. We are going to call the product x transpose y the scalar product. So note here that instead of calling this the dot product like we were before, we're going to use a little bit more formal term of scalar product. In a 5.4, we are actually going to have a little bit more formal of a term for this when we actually generalize this kind of concept to more vector spaces than just Rn's. There we're going to call it the inner product. So the inner product is sort of the most correct of these terms, but for the moment, any one of these terms will work. And so if we have x is technically a column of all x's, and y is a column of y's, then x transpose y, the scalar product, is going to be the product of each pair, x1, y1, x2, y2, and so on, then added all together. One kind of important result of this that the book doesn't really go into is if we switch the order of of the x and the y, and we look at x transpose y versus y transpose x, if we write this out, this is what we have up above, so x1 y1 plus x2 y2 through x in y in. And this one, well, now we're doing the y's and followed by the x's, so we have y1 x1 plus y2 x2, and so on, till we get to y in x in. Well, we're just multiplying numbers here, so we can actually switch the order of y1 and x1, and y2 and x2, and so on and so forth. These give us the same number. So even though it looks like there's an order to this, that the x is the one being transposed, it really doesn't matter which order we do it in. X transpose y is the same thing as y transpose x. And you can actually think about that in terms of matrix transposes as, well, if we take x transpose y and we transpose that, remember taking the transpose of a product means that we swap the order and take the transpose of each one. So we have y transpose times x transpose transpose, but then x transpose transpose is just x. So in a sense, from a matrix perspective, these are actually transposes of each other. But the transpose of a one-by-one matrix doesn't change anything. So we actually do get the same result. But it is kind of important that when we want to think of this as a scalar product, we can switch the order without having to worry about it. We are going to make use of that idea pretty shortly here. But before we get into something like that, I'm going to go ahead and do an example. Let's take some vectors. Specifically, we're going to look at problem 17. In fact, I'm going to be using these vectors a number of times throughout this video. In that problem, we have a vector x, which I'm just going to go ahead and write as a row right now. We have 4, 4, negative 4, and 4 transpose. So this is a vector in R4. We have a vector y, which is 4, 2, 2, 1. So both of these are columns technically in R4. We can take the scalar product of x and y. And all we need to do is we take this 4, we multiply it by this 4. That's the first, both of our first elements. Now we look at our second one. So we have a 4, and now we have a 2 over here. And that shouldn't be a comma. These are multiplied. Now we're going to take this negative 4 times this 2. And finally, we'll take that 4 times this 1. And now it's just a calculator question. We work these out. We have a 16 plus 8 minus 8 and then plus 4. And ultimately, we get 20 as our result. So we have just a single number that is the dot product or scalar product of these two vectors. When we take the scalar product of a vector with itself, it turns out that result is always going to be a positive number, and we can take the square root of it. So we are going to say that the length, or they're calling it the Euclidean length here. Another term for it that you've probably seen before is magnitude, is going to be given by this formula. And I'll just go ahead and write it out here. We're thinking of this as the square root of the scalar product. The square root of x transpose x. If x is actually written in terms of x1, x2, x3, and so on, then we can actually expand that out. So remember, when we take x transpose times x, we're going to multiply those first two elements together, but they're the same thing. They're both x1, so we get x1 squared. And then we multiply the second elements together, but they're both x2s. And we just keep going with that until we get to xn. So we get this square root of the squares of each element of x. The book decided to define most of its things in terms of just R2 and R3, and then talk about Rn later, but I don't really feel any reason to do that. Our definition just makes sense for Rn anyways. So we can write this out very nicely in terms of the elements of the elements of X. Let's go ahead and actually apply this to our vector X from. Actually, let me just make up an X. We'll say X here is going to be 4, 3 transpose. So this is a vector in R2. The magnitude or length of this vector. Notice that we are putting 2 bars around this. That's pretty standard to do. There are some contexts where people will just put 1 bar as if we're doing like an absolute value, but in linear algebra it's pretty standard to do the double bars. So we'll have this 4, we'll square it. We have the 3, we'll square it. When we add those together, 16 plus 9 gives us a 25. So square root of 25 is just 5. And really, what have we actually done here? We've taken a vector in the plane. We can represent a vector as an arrow starting at the origin and ending up at a point. Specifically, since it's the vector 4, 3, we're going to end up at the point 4, 3. So, yes, the height here is actually a little lower than the length down here. Just imagine that. But what are we actually saying? We're saying that the length of this line is actually 5. And in a sense, what we've kind of done here is we've used the Pythagorean theorem. So if this is a length of 4 here, a height of 3 here, then the hypotenuse has a length of 5. Okay. Now, I did call this a magnitude and length. We are, like we did with the inner product in 5.4, we are going to use a more formal name when we generalize this concept. We are then going to call it the norm of the vector. So keep an eye out for that. If I call it the norm at any point, this is what I'm referring to. It's just another term for magnitude at this point. But for now, length, magnitude, and norm are all synonyms. We can also actually use this idea to talk about the distance between points. So here, if we're thinking about x and y as vectors, or thinking about them as their points where their endpoints are, where they start at the origin and they end up at points x and y, then we can talk about the distance between those 2 points. So here, let's go ahead and draw another picture. We'll have a vector x. Say that's x there. And maybe I'll put y over here. Let me start at the origin so it actually hits it. We have our y over here. We end up at different points. What is the distance between these 2 points? Well, we can find that distance by thinking about these as, we can think about that this line up here as being another vector. If we take x minus y, we get this line up here. Specifically, we want the line that starts at the endpoint of y and ends up at the endpoint of x. Because what we're really doing is if we take y plus x minus y, we should get x. So if we follow y and then x minus y, we should end up at the same place that we got to if we just followed x. So this is x minus y up here. And all we're just saying is that the distance between those 2 points is the length of that vector. And so that's what our definition over here is. And again, this is something that works in any Rn, but all the intuition about it just comes from R2 and R3. That's why they do it that way. Sometimes we want to talk about the direction of a vector without worrying about its length. So what we do then is we pick a fixed length. We are going to say that if we just want to talk about pure direction, we're going to just take our length to be 1. We're going to define a unit vector. It's a vector with length 1. Whether we want to call that length or magnitude is up to you, but that's what we mean by a unit vector. Any vector can actually be turned into a unit vector. All we need to do, so if we start with a vector x, we can turn that into a unit vector by defining a new vector where we just divide x by its length. Its length is a number. We can just divide each of the components of x by this number, and we get a unit vector. As an example, let's go ahead and take that vector x from our problem 17. So this vector is 4, 4, negative 4, 4. Technically, it's a column vector. We know its length. Well, we can find its length. We don't know it yet. We're going to take the square root of 4 squared plus 4 squared plus negative 4 squared. Of course, the negative's not too important there. And then plus another 4 squared. And so what have we done in here? We have, well, 4 copies of 4 squared. So 4 copies of 16. 4 16s are 64. So we have a square root of 64. And, well, 8 squared is 64, so our result is 8. That means that if we take x and we divide it by its magnitude, if we take each thing in x and we divide it by 8, well, 4 over 8 is 1/2. We get another 1/2. Negative 4 over 8 is a negative 1/2. And we get another 1/2. So this is a unit vector. If we found the length of it using our formula for length, we would get 1. And we also have it in the same direction as x. It's just a scalar multiple of x, so it keeps the same direction as x. And so what we like to kind of say is that this vector is the direction of x. We kind of define the idea of what direction is in terms of those unit vectors. A unit vector could be considered just a pure direction, and instead of just talking, say it has a direction and a length of 1, we just say it's kind of a pure direction. There will be some context later where we're insisting on using unit vectors will make things a lot nicer, especially when we get into a lot of the orthogonalization type stuff and solving problems using orthogonal bases. But we'll get into what that is later. So if taking the scalar product of a vector with itself leads to talking about the length of a vector, what does it mean to have the scalar product of a vector with a different vector? Well, it really comes down to angle, surprisingly enough. If we take two vectors, x and y, and I don't know why it says non-zero here. This formula does even work if they are 0. But I guess in that case, we can't really talk about the angle very, very nicely. Maybe that's why. So if we have two vectors and we have the angle between those vectors, then the scalar product of x and y is equal to the product of their magnitudes times the cosine of the angle between them. If x and y are 0, well, these magnitudes are 0 in the first place, and so it doesn't really matter what angle we picked. We're just going to get 0 overall. But how do we actually show this thing? What does that really come down to? Well, it has to do with something we call the Law of Cosines. So we're getting into some trig here. So let's look at a picture. So we have, let's say this is the vector x. This is the vector y. We have our angle between them. And, well, we're using trigonometry, so we probably should have a triangle in here. We are going to make a triangle where this side over here opposite the theta is actually just the vector x minus y, similar to how we talked about distance or between 2 points before. From the law of cosines, if we have 3 sides of a triangle and we have an angle of one of them, then the length of the side opposite the angle, if we square that, so talking about lengths here, so we're talking about the magnitude. that is equal to the sum of the squares of the other two sides, but then there's a correction factor. So right now it kind of looks like we're using the Pythagorean theorem. And if theta was a right angle, then this correction factor is 0, so we don't even need it. But if it's not 0, then we also have minus 2 times the product of the magnitudes, or the product of the lengths of the sides next to the angle, times the cosine of that angle. This is the law of cosines. And we're going to use that in the context of vectors. Mostly just the fact that our magnitudes here, our lengths of our sides, are actually just scalar products. Scalar product of vectors with themselves. Which means that we can think of these in terms of matrix products instead of having to worry about them being about square roots and all that kind of stuff. Now I'm going to leave all this stuff alone. I'm just going to write it down as it is, because there's not really a lot that we can do with it right at the moment. In fact, you can kind of see that the magnitude of x times magnitude of y times cosine of theta, that's going to just stay as it is in our formula in the long run anyways. Everything else is going to change. This one is a matrix product, and we know matrix products are distributive. We can actually FOIL this out. This is, if we take first, we have x transpose x. We have our outside, so x transpose y. But we do have a negative from there, so we have x transpose y. I guess one thing that I didn't mention here is the transpose of a difference is just the difference of transposes. We can view this as x transpose minus y transpose. We also have minus y transpose x. And then we have a minus y transpose times negative y, so we actually have a plus y transpose y. And then we have all this stuff. And I just copied it down there for us. Okay, so what can we do now? Well, we can cancel terms. We can cancel that term with this term. Those are the same thing. In fact, we can cancel that with this. These two terms, those are actually the same term. Remember, we can swap the order of x and y without any problem. So x transpose y is the same thing as y transpose x. So really over here we have minus 2, so we still have a negative in front of them, but we have 2 copies, times that scalar product is equal to negative 2 times magnitude of x, magnitude of y, times cosine of theta, and of course we can cancel a negative 2 from both sides. That wasn't really too important. So x transpose y is just product of the magnitudes times the cosine of the angle between them. Let's do an example of this. Let's use the same vectors from problem 17. So x here, again, just as a reminder, we have 4, 4, negative 4, 4. We have y, which we didn't use the last time we used these vectors. It was 4, 2, 2, 1. We already saw x transpose y, the scalar product, is equal to 20. And we also actually found the magnitude of x. We found that to be 8. The magnitude of y we don't have yet, so we're going to have to find it. So here, magnitude of y is square root of 4 squared plus 2 squared plus 2 squared plus 1 squared. And you can kind of tell they pick numbers here to make this come out nicely, because if we add all those together, we get 25. So ultimately, the magnitude of y is 5. Now, what does that mean for us? Well, if we have x transpose y equal to the magnitude of x times the magnitude of y times the cosine of the angle between them, we can solve this. And usually this is actually the way we use it, because usually the angle is the hardest thing to get. And so we just use the scalar product, which has a nice formula, in order to solve for the theta. So cosine of theta is equal to the scalar product divided by the product of the magnitudes. Scalar product we already saw was 20. Magnitude of x is 8. magnitude of y is 5. 20 over 8 times 5, that turns into a 1/2. Now, what angle has a cosine of 1/2? We're going to look at angles between 0 and pi, or 0 and 180. It doesn't really... We could look at other angles if we wanted to, but we don't actually have to go outside of that range in most of the time. So, what angle has a cosine of 1/2 between 0 and pi? It's pi over 3. Or if we want to say from 0 to 180, it's 60 degrees. Same thing. But that's all we have to do. That's how we find angle between two vectors. And notice here, we use two vectors in R4. If we actually had an intuition for what R4 is like, this would actually make sense to us. That there are two arrows sitting there in four-dimensional space, and the angle between those arrows does mean something, and it actually is 60 degrees. And we could actually even talk about, say, equilateral triangles in R4. Something that has 60-degree angles in 3 different spots. Something like that. But this is really the way that we like to work in higher dimensions. We can work with vectors very nicely because they're just rows of numbers, or columns of numbers really, and then we can actually do all this kind of stuff pretty easily, even if thinking about what angles are might be a little difficult. A simple consequence of the last theorem is this name theorem. We call it the Cauchy-Schwarz inequality. And basically, we know that the cosine of an angle is always between 1 and -1, which means that if we multiply by the magnitudes of x and y, this is always between, well, the magnitudes. So we multiplied on each side by those magnitudes, and then negative of those magnitudes. In other words, if we just replace magnitude of x times magnitude of y times cosine, we know that is the scalar product, and it has to be between negative the product of the magnitudes and the product of the magnitudes. Or in other words, the absolute value of the scalar product always has to be less than or equal to the product of the magnitudes. Now, it might seem a little bit weird to actually state this as a named result. Why does this have a name to it? But it turns out that this inequality will be true even in the more general case of inner products that we'll talk about in 5.4. There we're going to be talking about products in vector spaces where these aren't represented by arrows, where they're very general vector spaces, and so angle doesn't really make any sense to us anymore. But we can still actually define something called an inner product that has certain properties, and we can still show that it will satisfy this inequality. In fact, that will actually allow us to kind of give a concept of what angle would mean in those vector spaces. Kind of using this inequality to say, well, we can talk about introducing a cosine of theta where it didn't exist before, and saying the angle would be what theta actually makes sense in that formula. But for the moment, we'll just leave it like this. It's just a kind of a special first case of the more general Cauchy-Schwarz inequality. One thing to kind of note here, though, is that this does also specify that this is an equal sign if and only if one of the vectors is 0 or one vector is a multiple of the other. In other words, if either of the vectors is 0, well, both sides are going to be equal to 0, where the product of 0 and anything is 0, and then the magnitude of the 0 vector is 0, so these will both be 0. If neither one is 0, then how is this ever going to be equal to each other? Well, that's going to be true when x transpose y is either the product of the magnitudes or the negative product of the magnitudes, in which case cosine is actually equal to 1 or -1. In that case, Well, theta is 0 or 180 degrees. And all that means is that our vectors either point in the same direction, or you could say they point in the opposite direction. Either case, those vectors will actually be multiples of each other. If we're in the case where two vectors have an inner product of 0, if x transpose y equals 0, well, that means that the product of the magnitudes of x and y times the cosine of the angle between them equals 0. If x or y is 0, then this will always be true. But if x and y are not the 0 vector, then the cosine of the angle between them has to be equal to 0 in that case. And what angle has a cosine of 0? Remember, we're working with angles between 0 and 180. In that case, theta is going to have to equal 90 degrees, or pi over 2 if you prefer. I'm not going to be too picky about angles here, about degrees versus radians anyways. We are going to say that two vectors that do have an inner product of 0, or a scalar product of 0, are orthogonal. Or as we kind of saw here, we can also say they're perpendicular. It's kind of related to the scalar product versus inner product and magnitude versus norm. For some reason, we have more formal terms that we use in a lot of contexts. But you can kind of think of orthogonal as being a synonym to perpendicular, at least until we actually get into 5.4 and we look at this in more generality. But even in those contexts, people will sometimes still call it perpendicular. But I'll try to stick with the word orthogonal, just to make it a little bit clearer, so we can actually get more used to that. So they're orthogonal if their inner product is 0, and when they're orthogonal, we'll sometimes use the shorthand notation x is perpendicular to y. This is a nice way of just saying x is orthogonal to y, or x is perpendicular to y. So, that's just a shorthand. Okay. What are some consequences of vectors being orthogonal? Well, one really nice context here. What if we take the sum of two orthogonal vectors and look at the square of their magnitude? Remember, square of the magnitude is just the inner product or scalar product of x plus y with x plus y. We can FOIL that out, kind of like we did before. So we have x transpose x, we have x transpose y, we have y transpose x, and we have y transpose y. But what do we have here? X transpose x is the magnitude of x squared. X transpose y, well, I'm insisting here that x and y are orthogonal. So that's 0. Same thing with y transpose x. That's also 0. So we can skip right to y transpose y, which, very similar to the x one, is just the magnitude of y squared. So we have this relationship that the square of the magnitude of the sum of x and y is just the sum of the magnitudes, sum of the squares of the magnitudes of x and y. This is frequently referred to as the Pythagorean law. Because what are we really doing here? We've got, let me make that a little shorter. We've got a vector x. Well, let me say that's our x. We're going to have y here. Now, these are orthogonal to each other. So we have a right angle here. And then x plus y is the vector from here to here. So we follow x and we follow y. And so we get the result of x plus y, and all this is really saying is that the length of x plus y is the length, or squared, is the length of x squared plus the length of y squared. It's really just the Pythagorean theorem in disguise. But notice that we can actually do this in any Rn. The Pythagorean theorem doesn't care if we're working in 87-dimensional space. It still works. And in fact, the way that we calculate these lengths scales up very nicely. We don't have to make up some brand new way of talking about lengths in those cases. We just have our length of a vector, which is the square root of a sum of squares, and it works itself out. Very nice. The last topic I want to talk about is the idea of a projection. So basically, we start with two vectors, x and y. And we kind of want to talk about how much of x is going in the same direction of y, and how much is going away from the direction of y. And note here, by the same direction, I'm not really saying that they're both, say, going in the same direction, but they can be going in opposite directions. So I'm just saying how much of x either goes the same way as y or goes the opposite way of y. And by going away from y, I'm actually talking about how much it goes in a direction that's perpendicular to y.